Similar polygons. Similar. We gotta shut that up. Corresponding angles are congruent. Corresponding angles are congruent. Corresponding sides are what? What do you think?
Supplementary? Congruent?
Proportional.
Proportion.
Gosh.
That's right. Supplementary refers to angles making straight lines. Okay, that's fine. Proportional, meaning they are not same sides. The angles are exactly the same though. Corresponding angles are exactly the same. Just because you have a smaller triangle doesn't mean the angle is any different. Okay, that's important. Scale factor. How do you find scale factor? Talked about that a little bit. Anybody want to take a guess? What is a scale factor? Can you give me an example? Those things on the maps that you read?
The key?
Not a key.
Compass radius.
Isn't it?
3 miles.
Yeah, 1 inch is to 3 miles. That's a scale factor.
It's in the key.
Okay, excellent, good job. Alright, so basically what it is a ratio of sides reduced. The ratio of the sides reduced. Basically. Okay. Theorem 6.1. Favorite thing. Perimeters of similar polygons. If two polygons are similar, then the ratio of their perimeters is equal to the ratios of their corresponding side lengths. Okay, so given two polygons, you're not sure they're similar, but you have their perimeters. The ratio of their perimeters is equal to the ratios of their corresponding side lengths. So if we know that they're similar, you can use that to help you figure out what the side lengths are if you have missing side lengths. So their perimeters, one perimeter is to another perimeter as the corresponding side is to another side, okay? Got it? So the perimeters are ratios that we can use. All right, having said that, let me draw this here. Example, this is number 4. This is DEF and G. And then we have a small one right here. This would be R, S, E, Q. And what it says is DEFG is similar to PQRS. So you're gonna write similarity statements. This right here is a similarity statement, but you're gonna write similarity statements about their angles and then also proportions for their sides. Alright, so what do you know about? You don't even need these pictures if you have this. Why is that?
Because of the, theorem 6.1.
Well, I mean, how would I write which angles are congruent, or excuse me, yeah, congruent and similar? Angles and sides.
Angle.
Based on just what this is saying, not looking at the pictures.
Corresponding parts.
Yeah, the corresponding parts they're in order, right? So angle D is similar to angle P, right?
Yas.
You can say equal or congruent because they are equal. Okay. And so on all the way down. So angle E equals angle Q, angle F equals angle R, and angle G equals angle S. They are equal if the two figures are similar. Okay, and then you can say the ratios are similar. So I can say DE is to PQ. Right? DE is to PQ as what? Yep, is to QR. And that's the same thing as FG is to RS and GD is to SD. Now in the book they use similarity symbols here, but angles are equal from figure to figure. In this case you would say congruent. We're not actually talking about the degree. Alright, example 8. This is B, E, C, 10, 12, 5. B, U, and T, 9.6. 8 and 4. Similar. Are they similar? Question mark. How would you know if they're similar? What do you do? Oh, sorry. Are they similar? Why? Yeah, all the angles are the same. But if we wanted to show, if we didn't have the angles listed up there, how would we show it? And this is what I want you to do. That's if they are similar, you can use that. I'm saying, let's not look at the angles here and say we don't know that they're similar. How would we figure out? Nate?
Proportional sideways.
Tell me.
What do you mean by, like,
How would I set it up? Tate?
8 over 10. 75. To 2 over 5. Or,
We want to set this up. 8 is to 10 as 9.6 is to 12 as 4 is to 5. Good. And 4/5 equal like tenths. Yeah. What about 9.6 over 12? What's that reduced to? Hmm? 4/5? Take out your calculators. Well, can't believe you're doing this. What's 9.6 divided by 12, Nate? Huh?
8/10.
0.8. That's 96 divided by 12. 8. So 9.6 divided by 12 would be 0.8. 4/5 is 0.8. 8/10 is 0.8.
That is true.
Calculator for that.
Nope, didn't even get it out. You didn't get it out. You got it now.
Okay. Example 16. Always. Sometimes. Or never. Talking about similarity here. Okay, not congruence. Always, sometimes, or never similar. A right triangle and an isosceles triangle. Always similar? Let's try that first. Or would a right triangle and an isosceles triangle always be similar?
No.
No, because the size of right triangle can be totally different, right?
That is true.
What about sometimes?
Yes.
They can be sometimes, that means they can't be never,
That is true.
right? See, a right triangle can be an isosceles triangle. Anybody need a picture for that, or are you all good? Who needs a picture? Okay. Here is a right triangle that has 3 different lengths. Could I shorten this to be the same as that? And then isn't that an isosceles triangle?
Yes.
So we can have a right isosceles triangle. So that would be sometimes. They're sometimes similar. Okay. Let's draw a story problem.
Yes.
This is number 34 in your book. I can't remember if this is the sun and the moon or... Oh yeah, this. Okay, I think it's the sun. The sun, we have the moon, and we have the earth. Okay? Sorry, hold on. So this is 90-degree angle here. This is the earth.
Looks like a car.
This is the moon. This is the sun. The radius of the sun is 432,500 miles. There's the radius of the moon. Distance from the earth to the moon is 240,000 miles. The distance from the earth to the sun is 93 million miles. Stop talking, or you can do the note-taking guy, Matt, or whoever you're talking to. Alright.
It was Cooper. It was definitely Cooper.
Alright, you have 2 similar triangles. Why are they similar?
Because like the center of the moon is a red. No, sorry.
Aren't all the angles the same?
Yes.
Yeah, all the angles are the same. This is parallel. These are parallel lines cut by a transversal, so these are the same. That's the same. Those are both right triangles, so they're similar triangles. So these are similar triangles. How would I figure out the radius of the moon? That's what we want. How do I find the radius of the moon?
I lied. Never mind. I have an idea what's going.
Okay, we'll come back to you. Nick?
You take 93 million minus 240 million. 240,000.
Okay, now we're not trying to get this, that's how you would get that piece, but this is not a triangle from here to here.
Well, I thought you did that to find like the difference between that one and never mind.
But we don't need that piece. I mean, that's not wrong, we don't need that piece.
Okay.
So what pieces of the triangles do you have?
The corresponding part.
Corresponding parts, you're looking for this radius. So this radius is to that radius, or we could do this radius is to this leg, as this radius is to this leg, right? Instead of the proportion and solve it, do it please, right now. X is to 240,000, as 432,500 is to 93 million. Figure out what the radius of the moon is, please.
Are these actual numbers?
Yes.
Oh, I was confused.
We took a tape measure, drilled to the center of the sun. So my next question while you're figuring that out is, how do we know what these numbers are? Since obviously we've never been to the sun. Proportion. We can see the sun, can't we?
Sure.
We can't see the sun.
Only when it's nighttime, we can.
That is true.
Also with trigonometry, we can figure it out as well. But we can totally find the distances using proportions and trigonometry. So in here, you're only using proportions. Okay. But they did this before we even went to the moon. They did this a long, long time ago. And they used trigonometry, the angles and shadows. Shadows of the sun. How they actually did part of this is they took two measurements on the earth, two different places. The shadow going through a well, the angle of that, and the shadow in another spot on the earth, the angle that it hits in that well. And they could totally figure out the arc distance from one point on the earth to another point. So using trigonometry. So math is important. It can give us exact numbers without actually taking a measurement from one point to another.
Well, why would they bother with that if we don't really need to know how far away the sun is?
Well, know how fast light travels, knowing distances from one place to another, knowing how long it's going to take to get from here to there. Either, and also on the Earth to prove that exact distances where you have to, in a car you'd have to drive around a mountain, through it, over it. How would we know exactly how far something is? We can fly there now, but before we knew that, before we knew how to fly, we could figure out how to do that. How far it is across the ocean? And then originally they thought the ocean was flat.
Where do they think the water went?
Huh? And that the Earth was flat. I mean, there's a lot. Math taught us a lot. Christopher Columbus knew the Earth wasn't flat. So, all right, what do we get?
1,000.
What, Rob?
1,116.13.
1,000?
2,000.
What'd you get? What do you guys get? Is that right? Is he right?
1,140.
Is he
Good
correct?
point,
Is my question.
Good point.
Yes.
Okay, good. Your assignment.
You got 12.
Page 376, 325, 31, next review, all odds. Okay?